Hello class, this is CSE 4600, section 62, chapter 2, part 1, week 3, fall 2024. So, last chapter we looked at the hardware of an operating system, the hardware of a computer, and the operating system that makes it all work. We also looked into a few system calls, and last video I may have mentioned you're gonna be working on a lab. I don't have it out yet because I want to make sure I get it absolutely right, so it's worth your time learning about. Okay? So that's why I haven't assigned a lab just yet. I really want to get it right. I want to get it right so it's absolutely worth your time learning about and then playing with. So, Chapter 1 is the overview of a computer system, a little bit of the history of computers themselves, the 4 or maybe 5 generations of computers, a little bit about system calls. Now we're gonna look at one of the most fundamental concepts related to operating systems, and that is the process. This chapter 2, is all about processes and threads. But first we're going to look at processes before we look at threads. So the most central concept of any operating system is the process. This is an abstraction of a running program. And it's through this that a computer can concurrently run multiple things, or at least think it. I'll talk about that in a little bit. All modern computers often do several things at the same time. And a good example is how your computer may have multiple programs running at once. You might have a web browser, you might have PowerPoint, you might have a Word document open, or several. You might have Discord open, you might have like PDF readers open, you might have all sorts of things open. In my case, I have OBS open, I have several instances of PowerPoint open as well. I also have several web browsers open, and it's not just Opera GX. It's at times I have like 3 different operatings. At times I have like 3 different web browsers. Not multiple instances of the same browser, but 3 different web browsers open at once. That's basically how bonkers things can get on my end. This might be not too far off from what you might do on a day-to-day basis, but the point is, and especially if your computer has been made within the last 10 years, basically your computer is able to handle all of that. Another example is how when your computer starts up, when the system is booted, a bunch of processes are started unbeknownst to you. And it's not like these are malicious. Well, at least I hope not. But these processes are also essential to the operation of your computer, such as one process to look for incoming email, another process to look for new virus updates, antivirus updates, a process that starts up for any program that you need to start up when your computer starts up, possibly other processes for, say, Windows Explorer, for example, the process that makes the taskbar operate smoothly. You have basically you have many processes on your computer, and it's not just the ones that are on your taskbar. In any multi-programming system, the CPU switches between processes quickly, and when it runs a process, it does so for only a couple of milliseconds, maybe a few tens of milliseconds, or maybe a few hundreds of milliseconds. Because the operating system switches between processes so fast, even if there is only one CPU core, which is not likely to be the case, I'll explain why in a little bit, even if there is only one CPU core, it will still look like as though your computer is running multiple things at the same time. This is called multiprogramming, and in the case of there's only one CPU core, this is sometimes called pseudo-parallelism. This is in contrast to true parallelism, where if you have multiple CPU cores, each core can run a process each. And if that's the case, then you really can run multiple processes at the same time. If it is the case that your computer was made within, say, the last 5 or 10 years, there is a very, very good chance that you have, say, one of the latest AMD or Intel CPUs with like 4, 6, 8, even more cores than that. AMD came out with the Ryzen line of CPUs back in 2017, and the top of the line was an 8-core, 16-thread CPU that only cost like $300 something, which at the time was considered bonkers because the norm at the time was like quad cores, and 8-core CPUs were just out of the price range for most people. And it's because that, and probably because now that we have all of this special hardware, that we have to also learn about parallel programming. That's its own subject, by the way. So anyway, ever since then, AMD came out with a 12 and 16 core CPU that costs up to like $700, but you can get it for as low as $500. If you look for the appropriate discounts. Intel's offerings, I'll admit I am not familiar with Intel's offerings. All I know is they are not too far off in terms of core count in comparison to AMD CPUs. Also, they might have better IPC than that of AMD. Pick your poison, because no matter what hardware we use, it's the same process either way, for the most part. Anyway, let's look at the process model. In the process model, all the software on the computer, and this may include the operating system, is organized into a number of sequential processes, or simply processes. A process is an instance of an executing program. This is going to contain all the values in the registers, the program counter, all the other registers it has, and so on. Each process has its own virtual CPU, even though the physical CPU is switching between different processes. Oh, this rapid switching between processes is called multiprogramming, and the switch itself, some textbooks call this a context switch. Here we have an example of 4 programs loaded into memory. Each program has its own program counter, and only one process is ever running at a time. It's just that the operating system is in charge of determining which process to run at any given time. For the most part, we're going to assume that we're talking about a single core CPU. Multi-core systems are its own discussion. That's like chapter 8. In here, only one process is running at a time because we only have one CPU core. But because it switches between them so fast, it provides the illusion of the computer running multiple things at the same time, even though it's running one thing at a time. When this process is swapped out for another process, whatever it was doing must be saved. So when the CPU switches back to that previous process, it'll just start off exactly where it had left off. And that's also a very important concept that I'll talk about in a little bit as well. So, as I said, we are mainly concerned with single core CPUs. Multi-core CPUs are their own discussion, but if you have a system with n cores, it means that you can run up to n processes at once. Let's look at the process model some more. With the CPU switching between processes, there are a few things that can happen, and one of them is this. The rate at which a process performs its computation will not be uniform and probably not reproducible. Thus, processes must not be programmed with built-in assumptions about timing, because you might be doing step 1 and then step 2, and then step 3 in a process, the OS says, okay, let's switch it out for another process. And then the new process is on step 31, 32, 33, 34. And then it's blocked, so it has to wait for I/O or something. And then that process is swapped out for another process. It's on step 61, 62. But then it has to do a subroutine back at step 31, 32. And then swap in our original process where we were at step 3. So we continue at step 4, step 5, step 6. Because how processes are swapped in and out, and because it might also be the case that you might have different amounts of processes running at once. Anything regarding timing, basically thrown out the window. As I said, the rate at which a process performs its computation will not be uniform, and thus we must not build our processes without any built-in assumptions about timing. Of course, there are exceptions to this, such as when you have audio and video between two different processes, and you have to make sure they're synchronized. However, even with all this, most processes aren't affected by the underlying multiprogramming of the CPU or the relative speeds of different processes. So here's a concept that is very important to know. Process versus program. Imagine you're tasked to bake a cake, and you have the cookbook laid out in front of you. You also have all the ingredients laid out in front of you. The eggs, the sugar, the flour, the oil, or maybe you're using butter. You have the cake tin, you have the parchment paper, you have all the mixing tools laid out in front of you. You are following the steps in this process of baking a cake. You have the batter. You are mixing up the batter, folding up the batter, adding whatever the recipe calls for to the batter. You are following this whole recipe step by step. You have the batter ready, and you're ready to pour it into the cake tin. And then your son comes in, screaming he got stung by a bee. What do you do? Well, here's what you do. You stop what you're doing so you can administer first aid to your son. So now you have to go grab the first aid kit. You have to remove that little bee sting. Maybe you have to go in with some tweezers, which is probably not advised because it might squeeze out more poison into the bloodstream that way. So you're going to have to go in with, say, a credit card to scrape off that bee stinger off of your son. And then you can apply a Band-Aid to the affected area. Maybe you have to apply the appropriate ointment for that. So now you have to go through this separate step-by-step thing of administering first aid. But when all is said and done, your son is all better. He's nicely recovering from that bee sting. And oh yeah, you had a cake that you were about to pour into a cake tin. Do you start over and start making a whole new cake? No, you don't have to, unless you left it for way too long. Then you may have to restart. But the point is this: right before you administered first aid to your son, you kept a note of where you are in baking. So when you're ready to continue with your cake, you don't have to start over. So I do have another analogy, but I'm gonna have to grab something for that first. So as another example, imagine you took on the arduous task of, say, building a Lego set. You're doing step 1, step 2, step 3. And, oh, wait, I'm late for class. Stop what you're doing. Drive to class. Come back later in the day. And what step did I left off at? So here's the key thing about processes versus programs. And it's this. You think of a process as an activity. The kind of activity that you can interrupt. The kind of activity that you can Save what you're doing so you can come back to it later. And this is why when processes are swapped for other processes, saving the state of that process is crucial. If you're building a Lego set like this, and you have to stop what you're doing, you keep track of where you were so you don't have to restart. Here is another key thing about processes versus programs. The recipe that you are following for that cake in that what if scenario, it doesn't do anything until you follow it. In the case of programs, a program on a disk does nothing until it's loaded into memory. Oh, and also another thing, if you have two instances of the same program, they are two separate processes, and that's because I guess you can imagine a scenario where you and a friend are building the two instances of the same Lego set, and you and your friend might be building at different speeds. So in the processes of building those things, you might be at different steps. So that's what's meant by two instances of the same program being counted as separate processes. Okay, so now we have process versus program out of the way. A program is just instructions that are not yet being followed. A process is you are in the process of following those instructions. And hence we call it a process. If you are building something, is that why we call it a building? Anyway, operating systems need some way to create a process. In very simple systems, or systems that are designed to run a single application, all the processes that will ever be needed are all created at startup. Though with most systems, we need a way to create processes during runtime, and there are 4 events in which this can happen. The first one is when the OS is booted. Here, several processes are created, some for interacting with the users, others that run in the background. These are called daemons or daemons. That example of a process waiting for incoming email, that's an example of a daemon. That is a background process that does something important for the user. And it's called that because the word demon comes from a Greek word that originally didn't refer to evil spirits. Rather, its original use meant something closer to guardian angel. Guardian angels watching out for you. Which is the reasoning behind why these processes are called daemons, or demons. The PS program in Unix can be used to show what processes are running. And the equivalent program for Windows systems, that is Task Manager. So we can create processes when the OS is booted. How about creating processes after that? We need a means of doing that. Often, a running process will issue system calls to create more processes to do its job. Say a process is expecting large amount of data over a network. One process fetches that data to store in a buffer. Another one removes that data to be processed. Of course, if you have a multi-core CPU, this process of processing data can go faster because one core could be allocated to each process involved here. In interactive systems, users can start programs by typing a command or clicking or double-clicking the appropriate icon for that program. Either way, you need to create a new process when you start up a program. In a command-based system, the new process typically takes over the window in which it was started. For Windows, a starting process typically doesn't have I screwed up. In Windows, a started process typically doesn't have a window, but usually such programs create a window, or possibly more than one. Okay, so we looked at 3 ways in which processes can be created. at the start of when the system boots up, when a process needs to create more of itself, or when the user wants to start up a program. The last one more applies to mainframes. Here, users submit batch jobs for the system, possibly remotely. When the OS decides it has the resources to run another job, it creates a new process and runs the next job from its input queue. So this last one is more for mainframes. In any case, a new process is created by having another process execute a process creation system call. That system call in Unix is called fork. However, we need to call execve if we want that new process to have a different program from the original calling process. Because remember, fork creates a clone of the calling process, and if we want that process to do something different from the calling process, we need execve. In Windows, that system call is called create process. However, it handles both process creation and loading the correct program into it. So unlike with Unix systems, in Windows systems, we only need to call one. We only need to call one system call instead of calling two separate system calls in Unix systems. Either way, after a process is created, the parent and child will have their own distinct address spaces, not necessarily the same program loaded, and any changes made to one process address space will not affect the address space of the other process. So now we have processes. They're gonna do their thing. Eventually, they're gonna finish their job, or they're gonna die trying. So at some point, a process is going to terminate, and it's gonna terminate under 4 different conditions. The first one is when the user wants to close a program. So when a user wants to close a program, or for example, a program is finished running and it automatically closes itself. The exit system call in Unix, or exit process in Windows, that tells the operating system that a process has finished its work. Screen-oriented programs support voluntary termination. Usually there is some X or button that you click on to close a program. Typically a few more things might happen before the program actually closes, such as, hey, do you want to save your work? Yes or no? So yeah, process termination, a process has finished its work, or the user wants to close a program. That either way, a system call is needed to tell the operating system, hey, we want to terminate the process. Processes can also terminate if they encounter a fatal error. The C compiler, it's CC. If you type that, and then you try to type a source file that doesn't exist, it'll display an error message and then exit. Screen-oriented interactive interfaces may display a message box saying what went wrong instead. Here's another way that processes can terminate. They can terminate due to a bug in a program, or they tried to do some illegal instruction. Wait, that's illegal, and then the program terminates. Some systems have processes that can handle these errors by themselves, so this would result in the process being interrupted rather than terminated. And another way that a process can terminate is if a process executes a system call that kills another process. This system call is called kill in Unix and terminate process in Windows. The process that calls the kill or terminate process system call may also need authorization to do that. If also a process creates its own child processes, if that parent process is killed, the child processes may also be killed, but neither Windows nor Unix systems work that way. An example is if you have some process that is really stuck on something and you just want to close it. You might, for example, go to Task Manager and Task. Also know it's processes because they're not called programs here, they're called processes. Type a name, publisher, or process ID to. It's cut off here. So since it's Windows 11 Task Manager, you use this program to see what processes are running on your system. And again, they're not programs, they're called processes. Because processes are a program, an instance, an abstraction of a program that's already running. Programs don't do anything when they're sitting on a hard drive. They only start doing something when they're loaded into memory and a CPU is running it. When a process creates another process, that process, those processes may be associated in a sort of family tree, and if those child processes create their own child processes, we have a process hierarchy start to form. In Unix systems, a process and its descendants form what's called a process group. So all of these processes may work together for something. When a user sends a signal from the keyboard, for example, it may be sent to all members of this process group associated with the keyboard. An example of a process hierarchy can be seen with a Unix process called init. Right after a Unix system boots, a special process called init reads a file reads a file that says how many terminals there are. And then init forks a process for each terminal, and then each one waits for someone to log in. When a user logs in, the login process executes a shell to accept commands, which forks its own processes to execute those commands. So we have a hierarchy of processes in Unix, but it doesn't really exist in Windows systems. Windows systems don't have a concept of a process hierarchy. So here, parent processes have a special token called a handle, and that's used to control its children. However, these processes can hand these tokens to other processes, thus invalidating the hierarchy. Process states. So section 2.1.5, each process is an independent entity, but sometimes processes need to communicate with other processes. That's also another interesting thing about processes. Because as far as a process is concerned, for the most part, it thinks it has the whole computer to itself. Until it needs to start communicating with other processes. So suppose we have this command here. Cat, chapter 1, chapter 2, chapter 3, pipe, that's that vertical line, grep, tree. In this command, there are two processes involved. The first process runs cat, and that concatenates and outputs tree files. The second one is called grep, and in this instance, it's selecting all lines that contain the word tree. Depending on how fast these two processes run, the second process may be ready to run, but have no input ready yet because the other process is still doing its work. In that case, the second process is going to block until input is available. So it's not going to do anything because it can't do anything. So it's blocked until that input arrives. So there are two ways a process can be blocked, and these two conditions are different. A blocked process cannot continue because it's waiting for input that's not yet available. This blocking is inherent to the problem. You can't process anything if there's nothing to process. Alternatively, a process can be blocked if the operating system decides another process should run. This is a technicality of the system, such as not enough CPU cores to go around. Or another process has been waiting for too long, it's time for that process to run. So, process states. There are three states that a process can be in. The first one is running. So, a process is actively using the CPU at that instant. The second one is ready. It's ready to run, but it's temporarily stopped. It's temporarily stopped to let another process run. Another one is blocked, unable to run until some external event happens first. And in this state diagram, we have 4 transitions or arrows. Let's look at the states first. The first 2 states, running and ready, are similar. In either case, a process can run, but with the latter case, with the ready state, it can't run because there's no CPU core to run it. In the blocked state, a process can't run even if it has a CPU core available. Okay, let's look at those transitions. There are 4 transitions in this graph. The first one is the transition from the running state to the blocked state. The operating system discovers the process cannot continue right now, and it's waiting for an external event. It goes from the running state to the blocked state. Transitions 2 and 3, those are going from running to ready, or vice versa. This is where the process scheduler decides another process should run next, and removes the process that's on the CPU from that CPU. So this is where processes are swapped in and out from that CPU core. The fourth one is the transition from block to ready. A waiting process gets the input it's waiting for, and it's ready to run again. This can happen right away or later if the CPU is being used by another process. There are more in-depth state diagrams than this. For example, this one's from Wikipedia. It might talk about other states such as created, terminated. Those are to signify, hey, a process has been made and a process has finished its work. We also have these 2 extra states called swapped out and waiting, and swapped out and blocked. These are if these processes are waiting for so long that another process needs to be allocated into memory, so these processes are swapped out, put somewhere else, so that memory can be used for other processes that are waiting. Similar case for blocked. So we have so this is another concept that you're gonna learn later on in operating systems. It's the concept of swapping out pages of a process's memory space. And also memory spaces memory is its own subject in operating systems as well. We're getting a little bit too deep into weeds by looking at the state diagram. The point is, running, waiting, and blocked, or I guess running, ready, and blocked, those are the 3 main states that this particular textbook deals with, though other textbooks may include created and terminated to signify the beginning and end of a process's life cycle. And I'm inclined to agree that the addition of created and terminated makes the life cycle of a process much more clear, because created is the birth of processes, terminated is the death of processes, if you want to think about it that way. To implement the process model, the operating system must maintain a table. This is called the process table. So this table has an entry for each process. Some textbooks call each entry a process control block, so I am going to use that term here. The process control block, or PCB, it's basically an entry in the process table that contains information about that process's state. What is in the program counter? What is in the stack counter? What is the memory allocation like? What is the status of any open files that process has? And so on. So the information, all the information in a PCB, that is essential to restarting a process exactly where it had left off. Each PCB entry in a system, it may vary from system to system, but this table gives you a good idea of what entries are required for a PCB. Process management information, registers, program counter, stack pointer, priority, process ID, for example, memory management, pointer to the next segment info, and so on, file management, user ID, group ID, working directory, file descriptors, and all that. So this is just to give you an idea of what information is needed to be included in a PCB. How does the CPU core run multiple processes? So associated with each I/O class is a location somewhere in memory called the interrupt vector. It contains the address of the interrupt service procedure. So suppose a process is running when a disk interrupt happens. That process's program counter, program's address word, and in some cases a few registers, are pushed onto the current stack. They're pushed onto the current stack by the interrupt hardware. The computer then jumps to the address specified by that interrupt vector. Afterwards, the software, and it's usually the interrupt service procedure, takes over. So, all interrupts start by saving the registers, often in the PCB for a process. And then this information is pushed onto the stack by the interrupt. And then this information pushed onto the stack by the interrupt is removed, and the stack pointer is set to point to a temporary stack used by the process handler. These actions cannot be expressed in high-level languages, so these routines, they're typically made in an assembly language. And assuming the operating system is written in C, when this routine is finished, it calls a C procedure to do the rest of the work for the specific interrupt type. Then the scheduler is called to see which process can run next. And the thing about this, a process may be interrupted thousands of times during its execution, but it will always continue its work exactly where it was before being interrupted. So, figure 2.5, this is a skeleton of what the lowest level of the operating system does when an interrupt occurs. So 2.1.7, modeling multiprogramming. When multiprogramming is used, we can improve CPU utilization. For example, if the average process computes only 20% of the time while it's in memory, then with 5 processes, in theory, the CPU should be busy all of the time. However, this unreasonably assumes that none of the 5 processes are waiting for I/O at the same time. So, if we assume that a process, in this example, is computing 20% of the time, then if we have 5 processes, then there's a 20% chance that all 5 processes are gonna be waiting for I/O at the same time. So, really a better way to look at CPU usage is from a probabilistic viewpoint. So here's how it goes. Suppose a process spends a fraction of its time, P. This is gonna be some percentage, expressed as a floating point value from 0 to 1. It's gonna spend a fraction of its time, P, waiting for some I/O to complete. With n processes in memory at once, the probability that n processes are waiting for I/O is going to be P to the nth power. If this happens, then the CPU will be idle. The degree of multiprogramming, that is the number of processes a single core CPU can accommodate efficiently, we use that to calculate our CPU utilization. So remember, P is the time a single process spends waiting for I/O. Given n processes, CPU utilization is going to be 1 minus P to the n. If processes spend 80% of their time waiting for I/O, then we need at least 10 processes to be in memory to get CPU waste below 10%. Because remember, one of the most important things about operating systems is that they must keep the CPU busy. Don't leave it idle for too long. This 80% here isn't unusual when you consider interactive processes are waiting for user input. And this percentage is often higher on servers. There are a few caveats to this, and it's this. This probabilistic model is merely it's an approximation. It assumes that all end processes are independent when, well, they're not. A more accurate model can be constructed using queuing theory. That is its own mathematical field, but the point is that these curves may be slightly different from the actual curve in reality. Again, we could use queuing theory, but the idea is that these curves give a good enough approximation, even though the curve might be slightly different from this. Again, it's merely an approximation. And now, we get to threads. So far, we have spoken about processes. These have an address space and a single thread of control. Oftentimes, it's desirable for processes to have multiple threads, as though they were their own processes. And you may have heard about threads in the past, and you have no idea what they're for. Probably made more confusing by the fact that when we have multi-core CPUs, they are spoken about as having, say, for example, 8 cores, 16 threads. A little bit confusing, possibly. And even more so when I made this PowerPoint slide, I guess the designer feature in PowerPoint latched onto the word thread, and it gave me like thread as in sewing. It's the wrong kind of thread here. But anyway, why threads? Why have threads? These threads, you can think of them as processes within processes. But why have processes in processes? Well, here's why. A program may have multiple things happening at once, and some of these things may block time to time. If we decompose a program into multiple threads that run quasi-parallel, or truly parallel if we have multiple CPU cores, if we do that, it makes the programming model simpler. So here's what threads add to the picture. However, let's see what makes threads different from processes. Threads that are part of the same process, they all share the same address space. They also share all the same resources. Threads that are part of the same process all share the same address space. That includes data and instructions. Threads are also more lightweight. It's easier to create and destroy threads than it is with processes, up to 2 orders of magnitude faster. When there's substantial computing in I/O, having threads for separate activities speeds up a program. So if one thread, for example, is doing something and it's blocked, then another thread, the CPU can switch to another thread as part of the same program. And doing that makes the program keep running. And here's another thing about threads. If you have multiple CPU cores, you can run multiple threads. So here's an example of why you'd want to have a multi-threaded program, or the reason why we have multi-threaded programs in the first place. Consider a word processor. Instead of having one thread for everything, you can have, say, 3 threads. One thread for keyboard input, another thread for displaying your entire document, and another thread for automatically saving the document. Consider what happens when you only have one thread. Whenever the word processor saves the document, anything that the user tries to type will be ignored until the program finishes saving your document. If the user makes changes to the beginning of a long document, the word processor must reformat all successive pages as it's displayed on the screen, before the user can type in anything. So if we have multiple threads in this case, the user could do some changes to the first page, maybe delete the first page outright. That's gonna cause the thread that displays the document to do a whole bunch of work, reformatting everything. Instead of that thread blocking any keyboard input from the user, well, that task of listening to keyboard input, that's delegated to its own thread. And then maybe after doing such a massive change, the word processor decides it's time to autosave, so that task is delegated to its own thread. It makes the whole program way more responsive. Oh yeah, and it also doesn't work with processes, because if it's separate processes, unless you get some way to get the processes to talk to one another, it's not gonna work, because they're probably gonna have different instances of the same program. They can't really talk to one another unless you make them talk to one another. These operations must be done at the same file, so it wouldn't work if these were separate processes, because they are separate instances of the same running program. Another example of thread's usefulness is in a web server. On most websites, a handful of pages are viewed more than others, so a system can cache the most viewed pages for easy retrieval. We're gonna see caching a lot, by the way. Remember CPU cache earlier? Yeah, we're gonna see caching a lot. So a server can have one dispatcher thread and several worker threads. When a request comes in, the dispatcher thread chooses an idle worker thread and it hands it the request. The worker thread wakes up and checks whether the request can be fulfilled from the cache. And if not, then it starts a read operation to get the page from the disk. The read operation blocks the thread until it's complete. So that worker thread can't do anything anymore until the operating system gives it the file it's looking for. So in that case, if we only had one worker thread and another request comes in, that server can't do anything until that requested web page is loaded from disk. However, we have multiple worker threads here. So if one worker thread is blocked and another request comes in, that dispatcher thread can just hand that new request to an available worker thread, and then it's gonna check the web cache, and then if it fails to find the page there, it goes to the operating system as well. So this is the beauty of having multiple threads. One thread might be stuck on something, and it's waiting for something else. At the same time, you have these other threads that are also available to do something. So in the system, the server is written as a collection of sequential threads. And we can think about these two threads' code as infinite loops. So the dispatcher thread has an infinite loop of get next request from a buffer, and then hand off that work to some dispatcher thread. From the dispatcher thread to a worker thread. The code for a worker thread is as follows. It's gonna wait for work. If it receives work, it's gonna look for the page in the cache. And if it's not in the cache, it's gonna have to read the page from the disk. And then it returns that page. And considering requests are coming in constantly from different clients, imagine how inefficient it would be if a web server was single-threaded. If a single thread had to wait for a request and then fulfill that request, and then potentially wait for the operating system to find that page on the disk, and then that single thread has to Yeah, imagine how nightmarish it would be if a single thread had to do everything. I gotta do everything around here. And then it slows everything down. This is why we have multiple worker threads. I guess another analogy that could be brought up, and there are several real-life analogies for threads. Imagine, say, a fast food restaurant. You have a manager and other workers. You can imagine the manager in this restaurant is analogous to our dispatcher thread, and the workers analogous to our worker threads here. So, for example, a worker who's putting together a burger, he might have to go to the fridge because he ran out of mayonnaise. All the while, another worker might be working on some other sandwich that doesn't require mayonnaise, and he's able to fulfill that order. Which makes you wonder how the Krusty Krab is supposed to operate with just 3 people. Anyway. It turns out this is just one way to construct a web server. The other 2 ways are as a single-threaded process, which, as we saw, is potentially inefficient, no parallelism, no performance gains from multi-threading. The third way is based on a finite state machine. So this system assumes there are non-blocking system calls. Basically, with non-blocking system calls, it just... Okay, let's talk about it like this. So this assumes there are non-blocking system calls. So the process is able to work on different requests, but it must save its state before working on a different request. The long and short of it is this ends up simulating multiple threads, but in a roundabout and difficult way. So, the classical thread model. Now that we have a good idea of how threads are useful, let's look at them more closely. The process model is based on 2 independent concepts: resource grouping and execution. And sometimes it's useful to separate them, and this is where threads come in. So far we talked about processes as this thing that has resources and it goes on the CPU core to run. Well, under the thread model, we don't look at it that way. Rather, we look at processes in a different way. A process has an address space containing data, text, other resources, child threads, open files, and so on. Putting these things together as a process makes managing these resources easier. The other concept is to look at processes as a thread of execution, or simply a thread. A thread has a program counter, registers, stacks. In this way, processes are used to group resources. So think of processes not as units of program execution, but rather units of resource allocation. And then, this way, we can think of threads as units of CPU execution. Threads allow for multiple executions to take place within the same process environment. To a large degree, that's independent of one another. Having multiple threads run in parallel is much like having multiple processes run in parallel. Except threads share an address space and other resources, whereas processes must share hardware. Like, they have to share a printer, they have to share disks, physical memory, and all that. Because of the lightweight nature of threads, sometimes threads are called lightweight processes. Oh, and the ability to run multiple threads in the same process, that's called multi-threading. There's that word again. Oh, by the way, Intel calls it hyper-threading. But the general term is called multi-threading. So, we're gonna compare processes versus threads. So here we have 3 threads, but in scenario A, we have 1 thread per process. In scenario B, all 3 threads are part of the same process. In A, each process has a separate address space with a single thread of control. In B, there's only 1 process, but there are 3 threads of control. The key difference is this. In A, each thread has its own address space, but in B, all 3 threads are sharing the same address space, so therefore there's only 1 address space loaded in. There's only 1 thing loaded in memory, not 3 separate things. Not 3 separate things loaded into memory. On a single core system, these 3 threads take turns running. Much like how switching between processes gives the illusion of multiple processes running at once, the same is true for threads. Oh, another thing that makes processes and threads different. With processes, we need protection. We need needs of protection. Protection. What do processes need to be protected from? Other processes. We need to make sure that one process doesn't accidentally overwrite the memory of another process. So we need that kind of protection. This does not apply to threads. So there are no protection mechanisms that are like that on the level of processes. Not only is this kind of protection impossible, but it's also not necessary, because threads are owned by a single user, and threads are made with the intent that they cooperate with one another, not compete for resources. Threads, therefore, must be able to share resources between one another. Though, even with all that, there are a few things that are unique to each thread, such as the thread ID. So, at the process level, there are several things that are shared between all threads. The address space, the global variables, the open files, and all that. However, there are a few things that are unique to each thread, such as the program counter, its registers, its stack, and its state. Keep in mind that think of processes as units of resource management. Threads are not this unit of resource management. So it's important to realize that threads have their own stack. Each thread will generally call different procedures, so their execution histories will be different between one another. So one thread may be doing step 1, step 2, step 3, and then has to jump to step 6, 7, 8. Thread 2 might be doing something different. Step 1, step 2, but it's doing something different, so it goes straight to step 5, step 6, step 7, step 9. Like that. It's kind of like a choose your own adventure book, but instead of following one possible path, you're following multiple paths within one process. So the process is following different paths. So that's why each thread must have its own separate stack. When multi-threading is available, a process usually starts with one thread. And this thread can create new threads by calling some library procedure, presumably called thread create. It's not necessary or possible to specify anything about this thread's address space, because it's gonna share that with the thread that created it. As part of this call, the name of a procedure can also be passed in to this thread create function. This effectively tells the thread what to do. Sometimes threads are hierarchical, but this is often the case because all threads are treated as equal. In any case, this thread create procedure, returns a thread ID, and that is used to identify which thread is which. When a thread has finished its work, it exits by calling another library procedure, something called thread exit. Some systems can have threads wait for other threads to exit. using something like thread join. This is based on something called the fork and join model, where one thread creates a bunch of child threads. That main thread waits for those child threads to finish their job, and then they join back with one another at some point in the future after each of those child threads have done their job. Fork and join. You might also see this in the context of parallel programming, as applied to processes as well, because this also applies at the process level. Because sometimes you need to create multiple processes, and sometimes the processes have to talk to one another, not necessarily on the same computer, but between different computers on the same network. Another common thread call is something like thread yield, which allows a thread to voluntarily give up the CPU so another thread is run. And this is because there's no clock interrupt to enforce multi-programming the same way there is with processes. Because there's no scheduling for threads the same way there is for processes, and because threads are made with the intent that they would cooperate with one another, if they are sharing the same CPU core, you need to manually program a means of swapping out, or, well, not necessarily swapping out, but you need to program in a means to tell threads, one says it's my turn on the CPU core, basically. As useful as threads are, they do add some complications to the programming model. Consider the Unix fork system call. If the parent process has multiple threads, does the child have any of those threads? What happens if a thread in the parent was blocked on a read call? Is there a blocked thread in both the parent and child? When a line is typed, does only the parent get it, or the child, or both? This same problem exists with open connections, and, well, there's even more to this. What happens if a thread closes a file that another thread was reading? What happens when a thread notices there isn't enough memory, starts to allocate some more memory, and in the middle of that, it's switched for another thread? Will that new thread try to allocate more memory, resulting in twice as much memory being allocated than expected? What happens if, for example, two threads are trying to add values to the same memory slot? Say there's a 31 in memory, and one thread tries to add 4 to it. At the same time, another thread tries to add 3 to it. It might be the case that one thread adds 4, at the same time another thread tries to add 3. So before that plus 4 is added properly, the plus 3 is added, and that result is recorded, and then it's overwritten. So one thread might try to add 4 to make the value 35, but at the same time, another thread just computed the value 34, and then that gets written. That is its own set of problems that we get when we add multiple threads, and there is a whole slew of solutions to that. What I have described here, when two threads are trying to write two different values into the same memory slot, that's called a race condition, and it's called that because these threads are trying to race one another to be last. Not first, last. Because in a race condition, last place wins. Think about that for a while. But for now, the next set of slides is going to be about the POSIX thread library, which is part 2 here. I have a preview of what those slides are like. This is going to be part 2 of chapter 2. It's all about POSIX threads, and this is a Unix library for creating threads in a program. there's like 60 different function calls needed. No, there's like 60 different function calls available in this pthreads library, but you only need a few of them to be able to create and destroy threads and have those threads do work. So yeah, these slides aren't quite yet done, but as soon as they're done, they'll be available, and they're gonna be part 2 of our discussion on processes and threads. For now, we're gonna end it here. The video is about an hour long already, so expect sometime this following week a lab that talks about how to use the fork system call to make another process. I'm gonna try to make it fun. I had intended to have you write a shell program straight away, but I'm still having problems to get it to work on my end. If I can't get it to work and explain it in a way that makes sense to you, how can I expect you to learn anything off of it? You know. So for now, I'm gonna end this discussion here, and then we're gonna, in part 2, look at how we can get threads, how we can get a multi-threaded program using a threading library. Oh, and by the way, pthreads is not the only way we can make a multi-threaded program. There is another way we can do that, and it's my personal favorite. It's called OpenMP, and the beauty of OpenMP is that it abstracts away a lot of the nitty-gritty detail regarding making multi-threaded programs. So all you really got to do is slap in a few directives into your program, and boom, your program is now multi-threaded. We might look into that if we have time, but I want to look into pthreads first, because, well, you know, maybe your first lab is going to be 2 parts. The first one is system calls related to making new processes, and part 2 is going to be system calls for making new threads. So your first lab might, I expect your first lab to be 2 parts. We're gonna work with system calls that make new processes, and then system calls that make new threads. Alright? So that's gonna be it for Chapter 2, Part 1. Chapter 2, Part 2 is gonna be more about the pthreads library and more beyond that. Oh, and that issue with processes, threads within processes, and those threads interfere with each other's work. We're gonna look into solutions to those problems in due time. All right. So hopefully you've learned something interesting about these things, and hopefully you'll learn more when we get to the labs. So anyway, that's gonna be it for now. I'll have a good week, and I'll see you in the next video. Take care.